Velocity and acceleration. Velocity is more often used in physics courses than speed. The direction of motion of an object is critical to problem solving. In the kinematics 1D unit, the average velocity in the x direction was defined as v average is delta x over delta t. And you can see here, it's a vector, right? Delta x with the arrow over it, and so is average velocity. The instantaneous velocity was defined as the limit as delta t approaches 0 of delta x over delta t. It was briefly mentioned that calculus could be used to find instantaneous velocity. In the kinematics 1D unit, you learn that the slope of a line is rise over run. In a position time graph, the slope equals delta x over delta t, or x2 minus x1 divided by t2 minus t1. So here's our graph right here, position, time, delta x is this right here, and here is delta t. And the slope equals the average velocity. So the slope is the very definition of average velocity. The slope of the line connecting 2 points on a position time graph is the average velocity of the particle in that time interval. Continue to decrease delta t until point 2 is infinitesimally close to p1, just as delta t gets infinitesimally close to 0. So what does that mean? Here's our delta t, right? And before, we had p2 somewhere up here. Now we keep shrinking delta t until p2 is right over p1. When we get there, the slope of the line at p1 is the instantaneous velocity. And that's what we're saying right here, the slope of that tangent line. That line is tangent to the position time curve at time t1. The instantaneous velocity is the limit of the average velocity as the time interval approaches 0. It equals the instantaneous rate of change of position with time. Repeating it, the average velocity equation was used as delta t kept decreasing until it almost hit 0, at which point the instantaneous velocity of the particle was found. We call that a limit, as follows. Right over here. So Vx is limit as delta t approaches 0 of delta x over delta t. And what is this over here, the dx dt? That is the derivative of x with respect to t. So now we're into calculus. The derivative calculates the rate of change of a function at a single point. In this case, the single point is represented by delta t approaching 0, and the function is the position vector. The derivative of graph function is also the slope of the tangent line to the function at that point. The derivative of the position is the velocity. The Calculus User's Guide, Derivatives, in the first unit of this course provides a summary of how to use derivatives. In the Kinematics 1D unit, velocity is defined as the change in position of an object over time. Velocity can also change over time. This quantity is called acceleration. Like velocity, acceleration is a vector quantity. Suppose the velocity of a particle changes from t1 to t2. The average acceleration can be found from the change in velocity delta Vx divided by the time interval delta t. So what do we have over here? Here's our equation. A average in the x direction is v2x minus v1x, which is delta Vx over delta t. There's your t2 minus t1. Looking at the equation, we see that the units of acceleration are meters per second over seconds, or meters per second squared. So acceleration is measured in meters per second squared. Define instantaneous acceleration using the same procedure that defined instantaneous velocity. The instantaneous acceleration is the limit of the average acceleration as the time interval approaches 0. So what does that mean? That's over here. Just like velocity and position, now we have acceleration and velocity. And the limit of delta Vx over delta t, as delta t goes to 0, is dVx over dt. The equations for displacement, velocity, and acceleration can now be used to calculate 2- and 3-dimensional quantities by using vector calculus. Example 1, average velocity. A toy car moves on a flat horizontal surface. From time t equals 0 to t equals 2, it travels 3 meters east, and from time 2 equals time 5, it travels 7 meters north. What is the average velocity from t equals 0 to t equals 5 seconds? Average velocity is the displacement of an object divided by the elapsed time of the motion. So here's our equation. And this is a little tricky, not too bad. We have to draw a triangle. Why? Because we need the displacement from our initial position here to our final position here. So we've got motion in the x direction and also in the y direction here. So the magnitude of the net displacement will be delta x1 squared plus delta x2 squared, and then you take the square root of that, it's just Pythagoras. And we get 3 meters squared plus 7 meters squared, square root of is 7.6 meters. So the magnitude of the average velocity is 7.6 meters divided by 5, or 1.5 meters per second. Average acceleration. An object moves on a flat horizontal surface. At time 3 seconds, its velocity is 3 meters per second west, and at time 4 seconds, its velocity is 4 meters per second north. What is the average acceleration of the object from t equals 3 to t equals 4 seconds? Average velocity is the change in velocity of an object divided by the elapsed time of its motion. And that's our equation right over here, Vf minus V0 over delta t. Find the vector value of the change in velocity. Assume west and north are positive velocities. So delta V is going to be V final minus V0, which is the same as delta V equals Vf plus a negative V0. On the vector diagram, add the vector of the final velocity and negative vector of the initial velocity. The resultant vector is the change in velocity. So that's our picture here. Here's our final. Here's the negative of the initial. And here's our delta V, which is what we're looking for. So the magnitude of the change in velocity vector is Vf squared plus V0 squared. Put in the values and we get 5 meters per second. The average acceleration then is 5 meters per second over 1 second, or 5 meters per second squared. And then to find the angle, it's the tan inverse of 3 over 4, which is 36.9 degrees, or east of north, right? North typically is up there, and here is east direction.